All right, so Solidity just released this new version 0.8.29, that ships this new syntax that allows you to relocate your smart contract's storage layout instead of having it by default starting at slot 0. In this video, I'll go through this new Solidity feature in detail so that you get a good understanding of it, but we'll also make it practical by looking at some EIP 7702 smart account implementations and look at how this new syntax can be leveraged in order to make them look much cleaner. So just a quick recap before we get started. You need to know that Ethereum accounts store their state in what we call storage slots. That's like 32 byte spaces identified by these slot numbers. Now, traditionally, Solidity assigns these slots sequentially, starting from slot 0, and places your state variables depending on where you put them in your smart contract. But let's have a look at what that looks like with an actual smart contract. So in this storage example contract, we have 4 state variables. And what Solidity does is that it automatically assigns these slots in the order that they are declared. So meaning first variable is being stored in slot 0 here, second variable is stored in slot 1, and third variable is actually also packed into slot 1. That is depending on packing rules, which I will not get into right now. And then slot 2 would be taken by the mapping variable. The point here is that this sequential layout is simple, but it can lead to kind of a messy experience when it comes to upgradability. And let's have a look at that next. All right, so all smart contracts upgradability patterns work a little bit like this here. Basically, you deploy a proxy contract that holds the state. And then that proxy contract points to a separately deployed implementation contract and delegates all calls to it. Then when you want to upgrade your smart contract, you basically upgrade the proxy to point to another implementation that you deployed. And then all delegate calls goes to the new implementation. Critical is obviously that this storage layer resides within the proxy contract and not the implementation, which means that the implementation must be compatible with the existing storage layout. So implementation v2 storage layout would have to be compatible with the prior implementation layout of implementation contract v1 here. So similarly to how proxies work, EIP 7702 upgradability allows a user to upgrade their EOA to become a smart account by introducing a special type of transaction that makes this EOA code field point to a specific smart contract wallet implementation. Now, similarly to proxies, these EOAs delegate every call to the implementation contract, and once they get upgraded, they point to a new implementation contract. But importantly, the state lies on the EOA level and not on the implementation contract level. Now, if you are unfamiliar with EIP 7702 and want a better understanding, I would pause here and check out the link in the description notes below, where I did a video that goes through EIP 7702 very much in detail. In any case, the point here about proxies and EIP 7702 upgradability is that both face the risk of storage collision. Storage collision occurs when the new implementation contract that the proxy or EOA upgraded to has a different storage layout than the prior implementation and thereby might override some existing storage values with new variables. But let's have a look at what this looks like on an actual smart contract. So let's look at this very simple example to understand how storage collision works. Let's say under EIP 7702, an EOA user upgrades their EOA to work as this wallet implementation v1. Now, after some time, the user updates it to wallet implementation v2. As you can see, the owner variable would be not affected here because it was sitting at slot 0 and still sits at slot 0 under implementation v2. However, the threshold now sits at slot 1 under the new implementation, and the nonce was residing here before under implementation v1. And this has obviously very dangerous consequences, because whatever value was stored as the nonce is now what the threshold in implementation v2 will take as a value. Finally, this last guardian state variable would not be affected because it would just be sitting at slot 2. Now, historically, smart contracts that were upgradable have dealt with this, among others, with this gap pattern, which allows a child contract to add storage variables even under future upgrades without overwriting any storage of the parent contract. Now let's say this is implementation v1. Now an upgrade needs to be pushed, so the child upgradable contract kind of needs a new variable. Let's say address public guardian. Now under this setup, the developer would have the responsibility to reduce the storage gap to 47 in order to keep track of it and not override the parent dummy variable here of the parent contract. Now, as you can see, even in this very simplistic example, it still requires like careful maintenance of this gap variable. And you can imagine that in complex inheritance setups, it requires a good knowledge about like Solidity's linearization inheritance, as well as storage packing in order to adjust the gap correctly. But in any case, this would not really work for EIP 7702 because EIP 7702 upgrades happen through various different entities. It might be dApps that push a user to upgrade their EOA to another implementation for their smart account, or it might be another wallet provider, and so on. And so this gap pattern definitely wouldn't work. A second, more robust approach here was introduced by ESC 7201, which defined a pattern for organizing contract storage into these isolated namespaces in order to avoid collision. And basically the way it works is that you define your namespace. Here in our example, it's account.storage, which is any string that then gets hashed. And here the account namespace has its own struct with related variables that belong to an account. And then you have these getter helpers, which return a reference to the account storage that resides in the smart contract state. And so whenever you want to set anything to the state, you get the reference and then set the variable that you want. Now this method works well because Ethereum's storage space is huge. It has 2 to the power of 256 minus 1 slots. And therefore the probability of any of these namespaces to collide is basically 0. But as you can see, we are using low-level assembly, and depending on how many state variables you have and so on, you can have a lot of these of this boilerplate. It's quite verbose and it's not ideal. Now, until now, before this new Solidity version that introduces this new syntax, this is the best way of doing things. And as you'll see here, for example, I have the EIP 7702 smart account implementation of Ambire Wallet open. And you'll see here that they do exactly that in order to avoid this storage collision. So first here so the contract is called Ambire account. And then we have this interface Ambire account, which defines this struct Ambire storage, which has this mapping of privileges and a nonce. Within the Ambire account, they create this constant Ambire storage position by hashing their defined namespace, which in this case is ambire.smart.contracts.storage. Now, as in our more simple example, they also use this getter, which uses lower level assembly in order to access the storage that resides at the hashed namespace. So whenever now they want to read a specific field of that struct or write to it, they would always call this getter in order to get the storage position and then read or write to it. Now here's another example I opened to showcase this. This is the kernel contract from ZeroDev. This is their implementation of an EIP 7702 smart account. This kernel contract inherits from the validation manager. And the validation manager, for example, has a bunch of other inheritance. But anyway, that's not interesting. But you'll see here that they use exactly the same pattern. We find this struct called validation storage. And this struct groups all state variables related to validations in the smart account. Now, if we search for this, we find this internal method called validation storage. So it's named a bit different here. It's not called get validation storage, but just validation storage. But essentially it does exactly the same thing here. It retrieves a storage reference to the validation storage struct, which is located at this validation manager storage slot constant, which is defined here in another file, but is basically the hash of the namespace for this validation manager storage slot. All right, so this was a long introduction in order to show you why this syntax and this new Solidity feature might come in handy. But now let's actually get to the point where I show you what this new Solidity syntax looks like. So this here is a good example. It basically comes in the form of layout at, and then comes the slot expression. And this syntax basically tells the compiler to start placing storage variables at the specified slot, which is 100 here. So in this example, we have a fixed size array of uint elements. Without this new syntax, by default, Solidity would place those 3 elements at slot 0, 1, and 2. But since we start the storage layout of this contract at slot 100 with this new syntax, this array would occupy slot 100, 101, and 102. Now, a few details that you might want to know. First of all, the slot expression here must be computable at compile time. And in case you have inheritance, it can be placed like this in front of your parent contracts. But important to know is that it applies to the complete inheritance tree, meaning that it shifts all storage variables by the same amount. So you can't have your own custom storage layout in your parent contracts. So let's look at how this new syntax could be used in order to make these EIP 7702 smart accounts much cleaner in implementation. Basically, how we would rewrite Ambire account is that we would just specify the storage layout to start at slot determined by the hash of the Ambire smart contract storage namespace. And then we would use state variables the way we are used to. The benefits are clear. We have direct access to our state variables without any helper functions that allow us to retrieve a reference to storage. There's no assembly code, and it's easier to audit and much more readable. This kind of wraps it up. I don't think it's a coincidence that Solidity decided to ship this feature just before EIP 7702 comes with Spectra on Ethereum mainnet. This provides, as we've seen, a very clean way for wallet providers to avoid storage collision when upgrading users' EOAs. I hope this helped to understand this Solidity feature better. If you have any comments or questions, please drop them below.